For the last few lectures, we are discussing about probabilistic algorithms. We have seen probabilistic algorithms for numerical integration, counting, and verification of matrix multiplication. And all those algorithms are classified as Monte Carlo algorithms. So, those probabilistic algorithms whose error probability can be significantly reduced by a small increase in the execution time. The agenda for today is to discuss about a Monte Carlo algorithm for the min cut problem. So, we shall see a Monte Carlo algorithm for the min cut problem in graphs. What is a cut in a graph? I hope you remember from the flow network topics we discussed about min cut. Given a graph with vertex set V and edge set E, here is an example. A cut is a partition of the vertex set into two disjoint non-empty subsets. In this case, the purple set and the yellow set. So, you just divide the vertex set into two disjoint subsets. And what are the edges crossing the cut? These are all those edges such that one end of the edge is in one set and the other end is in the other set. So, this is what we are telling. Edges crossing the cut are those edges xy such that x is in one set and y is in the other set. Example, here there are 4 edges crossing the cut. And why is it called a cut is, if you cut these edges crossing the cut, then you can separate the graph into two disconnected components. Between them, no connection. And the number of edges across the cut or crossing the cut is called the size of the cut. In this example, the size is 4 because 4 edges are crossing the cut. Now, what is min cut? Given this graph, min cut is a cut with the minimum size, the minimum number of edges crossing the cut. In this example, there is a unique min cut which partition the vertex set into this blue set and green set, and in the cut there are only 2 edges or 2 edges crossing the cut. We need an algorithm to find the min cut of a given graph, and there are many algorithms known in the literature which are deterministic. Given a graph with n as the number of vertices and m as the number of edges, complexity of the best non-deterministic min cut algorithm is upper bounded by n squared multiplied by m multiplied by log n squared divided by m, where n is the number of vertices and m is the number of edges. So, for a dense graph, when all the possible edges are there, m can also become order of n square. So, it is order of n to the power 4 multiplied by log n square divided by m. So, in that case, it will become 1, but it becomes order of n to the power 4 for a dense graph. That is the best non-deterministic solution. Question is, can we get a more efficient but randomized min cut algorithm? Answer is yes, you can. We can have an order of n square Monte Carlo min-cut algorithm. We can upper bound the complexity by order of n square if you go for a Monte Carlo algorithm. Recall that repeated execution of the Monte Carlo algorithm can reduce the error probability. If you allow a little more time, you can control the error probability to a greater extent. That is the property of a Monte Carlo algorithm. And we shall discuss a Monte Carlo algorithm for the min-cut problem. And the algorithm that we are going to discuss is depending on a graph operation known as edge contraction. So we are going to see a Monte Carlo min-cut algorithm using a concept known as edge contraction. So before we look at or develop that algorithm, let us see what is edge contraction. So given a graph, what is edge contraction? Contracting an edge, say xy, involves combine the end vertices x and y to a multi-vertex xy. So this is what I am telling. When you contract that edge, what you do? Combine the end vertices of the edge you are contracting into a single vertex. Now see that single vertex is representing two vertices in the graph, and so it is called a multi-vertex. Now what else you have to do? For each edge outgoing from x, in this case there are xu and xy. What you add? You add that edge from the combined vertex. If there is an edge going out of x, you add it from the combined vertex. You don't mind about y. All those edges leaving x in the original graph, you add it from leaving, add it like leaving the combined multi-vertex. For example, here, for representing the edge xu, you will add an edge from the combined vertex to u. Similarly, there is an edge leaving x but going to y. Both are here represented as a single vertex, so it is a self loop. Okay, similarly you do for y. So from y there is an edge leaving to u, so you are adding that edge yu, and from y there is another edge going to v, so you are adding this. I hope you are getting me. And after this you remove all the self loops added to the multi-vertex. So this is a self loop from xy to xy. You just remove it. So this is edge contraction. This is a simple operation to perform. You take an edge, contract it, meaning combine those end vertices and do all these four operations. And this is a notation saying that the graph G contracted with edge xy. So the edge contraction xy is applied on the graph G, that is this notation. And now see that edge contraction can result in a multi-graph. What is a multi-graph? A graph which allows multiple edges between vertices. If you look at this graph, between these two vertices there are multiple edges, in this case 2, and there can be any number of such edges. It is called a multi-graph. So what it leaves is a multi-graph. Now can we use edge contraction to find a min-cut in a graph? Yes, we can. And what we do? Observe that edge contraction reduces the number of vertices by 1. If you contract an edge, you can see that you are combining two vertices into a single one, so an edge contraction effectively decreases the number of vertices in the graph by 1. So that is what I am trying to tell. Now what you do? Repeatedly apply edge contractions until the resulting graph contains only two vertices. They are going to be multi vertices and the graph is going to be a multi graph. So you can do exactly n minus 2 edge contractions, then you will get a graph with only two vertices u and v. Both will be multi vertices. Let u and v the only multi vertices in the resulting graph after a sequence of n minus 2 edge contractions. So this is what I am trying to tell. You started with a graph, applied a sequence of edge contractions, resulted in a graph with only two vertices, u and v. Not that u and v can be multi vertices. And let k be the number of edges between u and v. This is what I am telling. You know that when you contract, multiple edges can get added between two vertices. In general, there could be a number of edges. Let it be k. Then you can see that there exists a cut with the size k in the input graph, that we can prove. If you cut all these edges, then you are actually partitioning the vertex set into a set of vertices in the multi-vertex u and a set of vertices in the multi-vertex v. We can run this concept on the example graph, which will make the process clear. So we are anyway getting a cut of size k. So the actual min cut will be of size less than or equal to k. Because we are getting a cut of k size, definitely the required min cut must have a size k or less. We can try to apply this concept on the example graph. This is the example graph G0. So what you have to do is you have to do a sequence of n minus 1 edge contractions. So here there are 8 vertices. So 6 edge contractions will give us a graph with only 2 vertices, and there you can get a cut. Contracting the edge 1 2, I am going to contract the edge 1 2 in the original graph, not that we are contracting the edge on the original graph. Okay, so look at the edge 1 2, contract it, you are getting this as the resulting graph, the graph G0 contracted with edge 1 2. So you are combining 1 and 2 into a single vertex, and what are the edges getting added? This is the edge representing the edge 1 7, and this one is representing the edge 2 7, and this one represents the edge 1 8 in the original graph, and the other one represents the edge 2 8 in the original graph. And not that you added the edge 1 2 as a self loop here and you removed it. Self loops are going to be removed. So this is the graph that you are getting after you do first edge contraction on the edge 1 2. So this is the graph that we have G1. Now apply edge contraction on the edge 4 5. You can see that you are combining and getting this as the resulting graph. You can verify it offline. So this is G2. Now we have G2. You do the third edge contraction, you are getting G3, and this time suppose you selected 3 6 as the edge. It does not matter which one you are selecting. 3 6, then you are getting this as the resulting graph G3. Then you take G3 and apply the fourth edge contraction, you are getting G4, and in this time you are contracting the edge 2 7 of the original graph. See that we are not actually applying edge contraction between this multi vertex and this vertex, but we are only looking at the edge 2 7 on the given graph and do that edge contraction. It will give you G4. You can verify it offline and take it. Now you apply the fifth edge contraction. Now I am selecting 5 6 as the edge of the original graph and I contract. that will give me G5. You can verify that what I am doing is correct. And now finally, in this case, I need to do one more edge contraction because 8 vertices are there, 6 edge contractions are required. And in this case, now I am contracting the edge 1/8 of the original graph, giving me G6. And now see that only 2 vertices are there, both are multi vertices. And now you can say that there is a cut of size 2. In one side of the cut in the original graph, you have the vertices 1, 2, 7, 8, and on the other side you have the vertices 3, 4, 5, 6. So on this graph, we got this as a cut with S as the vertex set in one side and V minus S as the vertex set in the other side, and which is having a size of 2. So this is exactly the cut that we got. And if you are selecting that sequence of edges, definitely you will get this cut. In this case, that is happen to be the min cut, but may not be true because it depends on which all edges you are contracting in the sequence of 6 edge contractions. And this gives us an idea for writing a Monte Carlo algorithm for min cut. What it is going to do is it selects edges to be contracted uniformly at random, and that is the randomness or the probabilistic approach that we are going to use. Now I am just copying the algorithm given in the text. So it's min cut Monte Carlo, and it takes a graph as input and it returns, these are parameters to return the solution, the first set of vertices and the second set of vertices of the required cut and the size of the cut obtained. And what does it do? It says that G0 is the given graph and the iteration count is set as 0 because it is actually I is representing the subscript here. It's 0, so you are initializing it as 0. And you are going to repeatedly apply edge contraction until you get a graph where the number of vertices, maybe multi vertices, is only 2. Until it greater than 2, you are doing it. What you do? This is the randomness. Randomly select an edge xy in the original graph. I can say it is E0. Okay, maybe I will change it to E0 because I will only select an edge in the original graph, but which is of course in the current instance of the graph when you do edge contraction. So saying this is also correct, but recall that we are selecting an edge which exists in the original graph. Now what you do? You say that the next version of the graph is the current version contracted with this graph, this edge xy. Then you increment I, the index, because you are getting the graph in the next iteration. So what will happen? Eventually, after n minus 2 edge contractions, you will get a graph with only 2 vertices, and then you will come out of the loop, where what you do? You say that the first set of vertices is the vertices in the first multi-vertex of the resulting graph, not that in the resulting graph only 2 vertices. Whatever be the set of vertices in the first vertex of the 2-vertex graph that you obtain, you say that S is that set and V minus S is the other set of vertices in the other multi-vertex. And what is the size? Size of the cut that you obtain is the number of edges in the final graph. Okay. So we have seen Monte Carlo min cut algorithm, and we can prove that the algorithm that we have seen here, it terminates. This is the only group, and that is easy to see because it will terminate exactly after n minus 2 edge contractions. Each edge contraction operation decreases the number of vertices by 1, which we know from the definition of edge contraction, and sequence of n minus 2, where n is the cardinality of the given vertex set, result in a graph with only 2 multivertices, and hence the algorithm terminates. And you can see that the complexity of edge contraction operation is order of n, because you are only looking at the vertices of the graph, then you are adding the required edges. So you are in general doing n minus 2 edge contractions. Each edge contraction is taking order of n. So order of n square algorithm you are getting. Now the question is that algorithm always correct? No, it is not. It can go wrong if at any point of time the algorithm is selecting an edge which actually crosses the required min cut. We don't know what is the min cut, right? And if no edge which is crossing the required min cut is selected during edge contractions, maybe you will get a correct solution, but that also is not guaranteed always. But if you select an edge which is going to cross the cut, definitely you will get a wrong answer, because actually when you contract that edge which crosses the cut, you are combining two vertices into a multi-vertex, which actually needs to be in two different subsets of the required cut. I hope you are getting me. Anyway, you are getting a cut of size k, and therefore the actual size of the required min cut must be less than or equal to k. So what you can do is you repeatedly execute the set min cut algorithm on the graph, and you try to get a better min cut. That is what you can do, and in that way it is a Monte Carlo algorithm. So we saw that if kappa is the size of the min cut, then that kappa must be less than or equal to the size of the cut that we found, because we already found a cut of size k. So the original size of the min cut or the size of the required min cut must be less than or equal to k. Now suppose the contracted graph G prime at any stage contains a cut where in one side you have only a vertex, combined vertex, where the only vertices are x and y, and now in the figure shown the number of edges crossing the cut is 1, 2, 3, 4, 5. So in general k. Now we can easily prove that in the original graph all these 5 or k edges are there. So why are you adding an edge to xy? Because it is an edge which falls on either x or y on the original graph. Then only you will add such an edge in the resulting graph when you do edge contraction. That you can easily see from the definition of edge contraction, and you can see that all these edges are present in the original graph, which either falls on the vertex x or on the vertex y, and the only edge which originally there in the graph getting removed is this edge, which will become a self loop after contraction, which we are removing. That doesn't matter because that's not going to take part in the cut, because it's not going to cross the cut, that is between two vertices in the same set. So I hope you are getting an outline of the proof that all the edges crossing the cut that we found are there in the original graph, and hence what we found is a cut. With this we are finishing this lecture. Today we looked at a Monte Carlo algorithm for finding the min cut in a graph. A cut is partitioning the vertex set into two disjoint subsets, and the size of the cut is the number of edges crossing the cut. So, we found a probabilistic approach using edge contractions, where you need to do a sequence of n minus 2 edge contractions. You can get a cut, and if you are lucky, in a single execution you will get the required min cut, but it is not always correct. But to improve the precision or to reduce the error probability, you can repeatedly execute that min cut algorithm on the same graph instance. Thank you.